for the first time in history, we get an image of one, and it looks like the prediction. So
Wow.
it's a remarkable thing.
It started with a whisper, a blurry ring of fire against the darkness of space, captured in 2019.
The other thing we've had is so-called gravitational wave detections. So these are colliding.
A first glimpse at something humanity had only dared to imagine. A black hole. That now famous image, a hazy orange halo around a pitch-black core, wasn't just a photograph. It was a promise, a doorway, proof that the unreachable could be seen, even if only in shadow. But no one could have predicted what would come next. No one could have guessed that buried within the noise and chaos of those 5 petabytes of telescope data was something more, something no human eye had ever seen. Not because it was invisible, but because we simply didn't know how to look. A quantum whisper turned into a cosmic roar. Through the marriage of quantum computing and artificial intelligence, a revolution has taken hold, not just in technology, but in our understanding of the universe itself. And at the heart of that revolution lies the black hole, once the most unknowable object in existence, now yielding its secrets through the lens of quantum AI. This isn't just about clearer pictures. It's about what happens when a machine begins to see what humans never could. And what it found left experts stunned. The original Event Horizon Telescope image in 2019 was a monumental achievement. 8 radio telescopes across 4 continents, synchronized to create a planet-sized eye, all focused on one cosmic titan, M87 star, the supermassive black hole at the heart of a distant galaxy. That image was a triumph of coordination, mathematics, and patience. 5 million gigabytes of data were stitched together by traditional supercomputers, coaxed into revealing the barest silhouette of the void. But what if the story had only just begun? Traditional computers, bound by ones and zeros, can only do so much. They're methodical, logical, deliberate. But quantum computers? They're something else entirely. They don't just process data, they dive into it, exploring every possible path simultaneously, peeling back layers that were once impenetrable. Where a classical computer sees noise, a quantum algorithm can see meaning, pattern, structure, and when those algorithms were turned loose on the original black hole data, everything changed. Suddenly, the ring of fire was no longer a blur. The accretion disk, the swirling luminous matter orbiting the event horizon, came into focus. The quantum-enhanced image revealed gradients of heat and density that had always been there, but hidden in plain sight. It wasn't just sharper, it was alive, dynamic. You could see turbulence in the flow. You could trace the energy in its spiral. Then came the shock. Polar jets, streams of particles launched at near-light speed from the poles of spinning black holes, had long been a topic of theoretical models. We'd seen their effects in distant galaxies, glowing like lighthouses across the cosmos. But now, hints of these jets were visible in the quantum-processed image. Wisps of energy rising from the disk, aligned precisely where the models had predicted. Faint, but unmistakable. That wasn't all. A strange brightness in one part of the ring, a subtle asymmetry, caught the attention of physicists. The region glowed brighter, as if the black hole itself were pushing light forward. And that's exactly what it was doing. It was a visual confirmation of something Einstein predicted over a century ago. Relativistic beaming. Matter racing toward us at nearly the speed of light appears brighter than matter moving away. The black hole wasn't just spinning, it was dragging space and time along with it. But then came the impossible. The shadow at the center of the image, the empty core we thought was pure darkness, wasn't entirely dark. Quantum AI detected the faintest whisper of light, subtle emissions too weak for traditional analysis. This wasn't noise, this was information. Radiation from magnetic reconnection events, sudden violent shifts in magnetic fields near the edge of the event horizon. Something once thought to be completely invisible was now faintly glowing. It was as if the black hole was no longer just being seen, it was being heard, felt, understood. Quantum AI had given us a new sense, a new way of perceiving the cosmos, and the most jaw-dropping moment came next. The photon ring, a circle of light that had only existed in equations, where photons, trapped by the black hole's gravity, orbit multiple times before escaping or vanishing into the abyss. This ring had been predicted, even dreamed about, but never seen. Until now. The enhanced image revealed a band of polarized light exactly where the photon sphere should be. But it wasn't symmetrical. The polarization patterns were skewed, tilted in ways that suggested something extraordinary. The black hole, it turned out, was spinning faster than anyone had expected. Nearly at the theoretical limit, its immense mass twisting space-time into a whirlpool. Frame dragging, another of Einstein's wildest predictions, wasn't just happening, it was visible. And so, one by one, the laws of physics weren't just holding up, they were performing in real time before our eyes. The no-hair theorem, the structure of accretion disks, the mechanisms of jet formation, all were being revisited under this new lens. Because where classical computers had once been blind, quantum AI now saw with terrifying clarity. This wasn't just a better
For the
image.
first time in
It was
history,
a
we get an
key,
image of one.
a portal.
And it looks
It
like
was the first real glimpse of the edge of reality. The implications were seismic. Astronomers, cosmologists, particle physicists, they weren't just poring over
The other
images
thing we've
anymore.
had is
They were rewriting
so-called gravitational
a
wave
machine
detections.
born from
So
quantum
these are
mechanics and trained by algorithms had peeled back the veil on the most mysterious force in the universe. Not with brute force, but with elegance, using possibility itself as a tool. And the question that lingered wasn't just, what are we seeing? But what comes next? Because this was just one black hole, one snapshot, and the cosmos is full of them. Wait until you see what happens when this technology turns toward our own galactic center, towards Sagittarius, a star, the supermassive black hole at the heart of the Milky Way. The image we thought we knew, the blurry orange ring unveiled in 2019, was just the beginning. That historical image, as momentous as it was, merely hinted at the vast complexity hiding beneath the veil of cosmic silence. Now that veil is lifting, and it's happening thanks to something that, just a decade ago, existed mostly in theory: the marriage of quantum computing and artificial intelligence. The result isn't just an upgrade, it's a revelation. Because for the first time, we're beginning to see not just the shape of a black hole's shadow, but the intricate choreography of magnetic fields, light polarization, and relativistic forces swirling just outside the point of no return. At the heart of this technological leap is quantum AI, a system that doesn't think like a human or even like a classical computer. It doesn't sort through information step by step. Instead, it dives into possibility itself. Where a classical computer follows a single path through data, quantum algorithms travel all paths at once. That's not science fiction. It's quantum superposition at work. And when applied to the Event Horizon Telescope's massive datasets, it doesn't just speed things up. It uncovers what was previously invisible. Details buried in noise, signals washed out by uncertainty, patterns so subtle, no human eye or classical algorithm could ever have found them. When these quantum-enhanced techniques were applied to the original M87 star black hole data, something extraordinary emerged. The once fuzzy ring gained structure. It wasn't just a band of glowing gas anymore. It had ridges, fluctuations, temperature gradients, and brightness differentials. The very material orbiting the event horizon was mapped in detail. Regions of intense brightness hinted at the speed of matter, some of it moving toward us, some away, but all of it bending under the titanic pull of gravity. One area in particular glowed far brighter than the rest. Why? Because that's where matter, swirling toward us at near light speed, compresses light through a phenomenon Einstein predicted a century ago. Relativistic beaming. We were watching relativity play out before our eyes. But the most shocking part wasn't in the ring. It was in the darkness. The shadow at the center, once thought to be devoid of any signal, wasn't truly empty. Faint emissions, subtle fluctuations, and whisper-thin streams of polarized light began to surface. What could possibly be creating them? One possibility stunned the astronomical community: magnetic reconnection events. These are violent realignments of magnetic field lines. Explosive releases of energy akin to solar flares, but happening just above the event horizon of a black hole. Imagine the kind of magnetic violence needed to create a signal strong enough to escape from that close to the edge of forever. That's what quantum AI was revealing. For the first time, we were watching the magnetic heartbeat of a black hole. And then came the polarization ring, a feature that, until now, had only existed in simulations. This wasn't just a visual cue, it was a signature. Polarization tells us how light vibrates, and in turn, it reveals the orientation of magnetic fields. The data revealed a full ring of polarized light encircling the black hole's shadow, exactly where theorists said it should be, the photon sphere. That's the region where gravity is so extreme that light itself can orbit the black hole multiple times before being flung outward or pulled in. It's one of the most exotic predictions of general relativity, and now there it was, staring back at us. More than that, the polarization wasn't symmetrical. It showed clear directional bias, suggesting that the black hole wasn't just spinning, it was spinning near the edge of physical possibility, faster than we thought, almost as fast as theory allows. This revelation forces us to reconsider many of our models. When a black hole spins that fast, it drags space itself around with it. That's not metaphor. That's frame dragging, a warping of space-time that pulls everything, even light, into a spiraling dance. The implications ripple outward. It changes how jets of plasma form, how matter accumulates, how black holes grow, and possibly how they connect to the fabric of the universe itself. What happens to the so-called no-hair theorem in light of this? That famous rule claims that black holes are simple. They can only be described by three properties: mass, charge, and spin. But the quantum-enhanced data suggests there may be more to the story. Subtle differences in light emissions and magnetic behavior suggest complexities that might challenge the elegant simplicity of that idea. Are we seeing signs of hidden structure? Internal chaos? Something about black holes that no equation has captured yet? The door has cracked open. Behind these breakthroughs is an equally awe-inspiring story of human ingenuity. The Event Horizon Telescope isn't one telescope. It's a planet-sized instrument, a global array of radio observatories from Antarctica to Spain, from Hawaii to the South Pole, all watching the same celestial target. To collect the data needed for the original image, these observatories gathered petabytes of information, more than 5 million gigabytes. Too massive to send over the internet, the data was physically transported on hard drives to a central location. And yet, even with all that data, traditional algorithms had to make guesses, fill in blanks, smooth over uncertainties. That's where quantum AI changed the game. It didn't guess. It found the answers buried in the chaos. The real genius of quantum algorithms lies in how they treat uncertainty. Where classical computers treat noise as a problem to eliminate, quantum processors see it as a canvas. Patterns hide in noise. Correlations nest inside randomness. Quantum systems can evaluate millions of data relationships at once, finding real signals that classical systems would have considered lost. That's how the hidden polarization ring was found. That's how the inner emissions were mapped. And that's why this isn't just a prettier image, it's a deeper one that challenges what we believed about how matter, energy, and space-time interact at the most extreme frontier of physics. These revelations don't just deepen our understanding of black holes, they redefine it. For years, astronomers believed we were approaching the limits of what observation could show. Now the boundary has shifted. We're looking at the edge of a black hole, and we're not seeing darkness, we're seeing detail, motion, complexity, life in the void. It's enough to make you pause and reconsider everything you thought you knew about the universe. And it's just the beginning, because the next target is us. The next run of the Event Horizon Telescope, already being planned, will focus on Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. With upgraded observatories and quantum-optimized algorithms, the hope is to capture an image not just of a distant galaxy's monster, but of our own, the heart of our galaxy, the anchor of our night sky. What will we see when we peer into that abyss? The image we now have of M87 star is not just an aesthetic triumph, it's a scientific turning point. For decades, black holes were theoretical constructs, invisible entities defined only by equations. Then we saw one, and now we've seen deeper. The new quantum-enhanced image reveals more than light. It reveals motion, structure, and the interplay of forces that until now existed only in simulations. At the core of this breakthrough is our improved understanding of plasma behavior near the event horizon. With the polarization ring now clearly visible, scientists can track how magnetic fields twist and evolve in real time. These fields are not passive. They're actively shaping how matter flows into the black hole. They are powerful enough to extract energy from the black hole's spin itself, launching vast jets of material out across intergalactic space. These jets span thousands of light years, and they begin just outside the event horizon, in a space smaller than our solar system. The precision of the image now allows physicists to model the launch point of these jets in detail, and that could change how we understand galaxy formation itself. Here's why that matters. Supermassive black holes like M87 star don't just sit quietly in the centers of galaxies. They shape everything around them. Their jets regulate star formation, heat up galactic gas, and sculpt cosmic structure on a grand scale. But the exact mechanics of how these black holes interact with their galaxies have always been murky. The new image changes that. It shows the structure of the magnetic fields responsible. It shows how the inflowing plasma twists into helical patterns before erupting outward. These details give us the missing pieces we need to build accurate models of galactic evolution, models that don't just simulate what the universe looks like, but explain why. Even more profound is what the data says about gravity itself. According to general relativity, the region around a spinning black hole, what physicists call a Kerr black hole, should drag space-time with it. This frame-dragging effect is subtle, but in the new data, its effects can be inferred through the behavior of the polarized light. The direction and intensity of that light varies in a pattern that aligns with predictions of warped space-time. For the first time, we are observing space-time being twisted, not metaphorically, but literally. That observation is direct evidence for one of Einstein's most extreme predictions, and it's only visible because of the precision granted by quantum AI processing. The implications stretch beyond astrophysics. The success of quantum AI in enhancing these observations is a proof of concept. It shows that quantum computation isn't just a laboratory curiosity, it's a working tool, a tool that can process unstructured, noisy, real-world data and extract physical truths. This has consequences far beyond astronomy. It could accelerate research in climate modeling, material science, and even medical imaging, anywhere the data is too complex or chaotic for traditional computers to decode. But the black hole image also raises new questions. For one, the brightness asymmetry in the ring, one side glowing more intensely, confirms the black hole is rotating, but we still don't know exactly how fast. Some models suggest it's spinning near its theoretical maximum, others leave room for a slower rotation. The more precise the image becomes, the more we'll be able to constrain that value. And knowing the spin is critical. Spin affects everything, from how the black hole consumes matter, to how it grows, to whether it can generate gravitational waves during a merger. There's also the issue of black hole interiors. We can't see inside the event horizon, of course. Nothing escapes from within it. But the edge, the region just outside it, is now more visible than ever. And the light patterns emerging from that region may give indirect clues about the geometry inside. Some physicists even speculate that quantum fluctuations near the event horizon, what Stephen Hawking called quantum hairs, could imprint subtle features onto the light escaping the black hole's vicinity. If that's true, then future quantum-enhanced observations may be able to test ideas from quantum gravity, even hint at the nature of the information paradox or the structure of space-time itself. What's next? In short, Sagittarius A star. This is the black hole at the center of our own galaxy. Unlike M87 star, it's much closer, just 26,000 light-years away, but also much smaller, which means it evolves faster. Matter around it orbits in minutes, not days. That speed makes it harder to image with clarity, but also more scientifically valuable. With upcoming improvements in both telescope resolution and quantum-enhanced reconstruction, Astronomers believe they'll soon capture a much sharper, dynamic image of Sagittarius A star. Not just a snapshot, but a time-lapse. A real-time movie of matter circling the event horizon. That could let us test general relativity in motion, frame by frame. Ultimately, this isn't just about one image. It's about how we see the universe. For centuries, we relied on telescopes that collected light. Then we developed detectors for invisible radiation, X-rays, gamma rays, neutrinos. But now we're in a new era, the computational imaging era, where data and computation are so advanced, they become part of the telescope itself. The black hole image is not raw light, it's a hybrid product of observation and computation. And with quantum systems entering the equation, we are beginning to unlock layers of the cosmos we didn't even know were there. It's a reminder that discovery doesn't always require new telescopes. It sometimes requires new ways of thinking. And now thinking itself is evolving. Quantum AI isn't just a better calculator. It's a fundamentally new form of pattern recognition, one that mirrors the complexity of the universe it's helping us explore. That's why this image of a black hole isn't just about what we see. It's about what we're becoming. Creatures capable of using the most abstract ideas of physics and mathematics to turn silence into knowledge, darkness into structure, and impossibility into fact.